So hello there, let's start to review the chapter sound. So the first problem, as you can see it here, it states the speed of sound at 0 degrees centigrade is 331 meters per second. What is the speed of sound at 25 degrees centigrade? So make sure that like you went through the whole material, the lecture part, and then now we are in the review part. So now it says like, so speed of sound, as we know, like speed of sound can be calculated using the equation. So first of all, what are our given parameters? So our temperature is given as 25 degrees centigrade. But the thing is, then now what is V at this temperature? So you can apply the equation V equals 331 in meters per second, of course, multiplied by square root of T over 273. Okay, and of course this is in square root, where T has to be is absolute temperature, in Kelvin. Okay, then the first thing that we need to do to apply this equation directly, then we need to find the temperature in Kelvin. So we know that like temperature in Kelvin is temperature in centigrade plus 273. Okay, so you have that 25 plus 273 is going to be 25 plus 273 is 298 Kelvin. Okay, then once you found that, then you can apply the equation, which is 331 square root of 298 divided by 273. Just apply this equation, nothing else. So if you do the work properly, then what you're going to get is 298 then it's approximately equal to 345.8 meters per second. Okay, just a simple application of like the equation that we saw. And then the second example is, now you're asked to determine the speed of sound. So first, what are your given parameters? I like to go through like those steps, like what are my given parameters and so on and so forth. So the given parameter states that like the density of a certain metal, then its density is given as 7.2 times 10 to the power of 3 kilogram per meter cubed. Okay, and has a Young's modulus 10 times 10 to the power of 10 Newton per meter squared. What is the speed of sound in this metal? So V in this metal is equal to how much? So we know that like so when you come to the solution, then you should know what proper equation you will want to use. So the speed of sound in a fluid or in a solid can be found using V is the square root of the elastic property divided by inertial property, right? So the elastic property in this case is the Young's modulus, and the inertial property is just literally the density. So if you substitute those values, then the Young's modulus given as 10 times 10 to the power of 10 Newton per meter squared. Everything is in SI units. Then as a result, your V will also be in SI units, which would be in meter per second. So 7.2 times 10 to the power of 3 kilogram per meter cubed. Okay. Then if you apply this equation properly, And if you do the simplification, you plug those values in your calculator, then you should get the value. I mean, you can work it out together if need be. So I have 10 power of 10 times 10 to the power of 10 that you divide it, you plug in it in your calculator, then if you do it properly, and then you square root it, then the speed of sound in this solid material is approximately 3,726 meters per second. Okay, please go ahead and verify if that is a correct answer. Then you can go to the next problem. The next problem states that, like, how far away is a lightning strike if you hear the thunderclap 3 seconds after you see the lightning? So the speed of light is 3 times 10 to the power of 8 meters per second, which is way larger than the speed of sound. So as a result, like, you know, we're going to neglect like, you know, the distance traveled by, or the time traveled by the lightning can be neglected. Just let's consider that, like, the time taken by the light to travel that distance is pretty much neglected, and we can just simply focus, for this particular case, we can just simply focus on the sound. Just let's say we saw the light, and then after that we heard the clap. So if we consider, or if we take our simplified model, we'll just simply consider, you know, you have speed of sound, which is 340 meters per second, and then the time taken by that sound is 3 seconds. Then on average, like, how much distance usually represented by S or D, is how much? So S is like just average speed multiplied by time. So the average speed of the sound is going to be considered at 340 multiplied by 3. Then that's going to give you 1020 meters. Okay, so we're ignoring the impact of the light. Okay, so the second question, or I mean the fourth question, is about the intensity level of sound with intensity. Now it's given as intensity level. Now that's what we are trying to find now. So the next problem is, what is the intensity level? So make sure that, like, the problem states intensity level. Then you'd expect your answer to be in decibels. Okay, intensity level of sound with intensity of 5 times 10 to the power of minus 10 watt per meter squared. So now you know that your given parameters, again, given, use the blue, your I for intensity is 5 times 10 to the power of minus 10 watt per meter squared. I naught, which is the intensity at threshold of hearing, is 10 to the power of minus 12 watt per meter squared, right? Then what you're asked to determine is the intensity level, which is represented by beta. So we know that beta equals 10 times logarithm of I over I naught. Okay, so then the value of beta is going to be 10 into log I is 5 times 10 to the power of minus 10 divided by 10 to the power of minus 12. Okay. So if you do some exponential trick here, what you will have is like 10 into logarithm of 5 times 10 to the power of minus 10 plus 12 on the power. So the power, when it goes from denominator to numerator, it's going to be a plus, right? So then you will have beta equals 10 times logarithm 5 times 10 minus 12 is, of course, minus 10 plus 12 is 10. So just simply substitute like 10 into logarithm of 5 times 5 10 to the power of 2 is like 500. So logarithm of 500 will be, so you plug it into your calculator and check like how much would be that. Then log 500 is approximately 2.69 or approximately 2.7. Then your beta value will be 10 times this value, which is to be 26.9 decibel. Okay. Let's go to the fifth question. So the fifth question is Doppler's effect. Okay. So in the Doppler's effect question, first of all, we saw 3 different scenarios. One is when the source is moving while the observer is stationary. Second one is when the observer is moving while the source is stationary. And there's also a general case, what if both are moving, and so on and so forth, or just like something that really keeps everything as a general equation. So here number 5 says a train station bell goes off with a fundamental tone. So the bell is your source, so you're given, so the frequency of the source is given as 500 Hertz. As the train approaches the station, so the velocity of the train so that means like the observer is now moving. Okay, so a moving observer, and which is 20 meters per second, because the person who's riding the train, how much frequency will he hear if Vs, or the speed of sound, is 335 meters per second. Okay, so in this particular case, it's up to you, to choose what equation you want to use. But the equation that I provided in the lecture part, so it says like if it is the observer that is moving, okay, then you can use the equation, the frequency heard by the observer equals the frequency of the source into v, the speed of sound, plus v naught divided by v. Okay, v represents the speed of sound, so, and then keep in mind how to use v naught. V naught in this case is positive, because observer is moving toward the source, Okay, so f naught equals then fs, which is the frequency, that is 500. V is the speed of sound, 335, plus 20, the speed of the observer on the train. Divide that by 335, and if you simplify this, then you will have 500 multiplied by 355 divided by 335. Then frequency heard by the observer will approximately equal to 530 Hertz. Okay, everything in SI unit, then your final answer will also be the SI unit in SI unit. Number 6. Number 6 states, you stand by the railroad tracks as a train passes by. You hear 100, so frequency 1000 Hertz of the source. When the train approaches, we change to 100 Hertz as it goes away. So you're given two frequencies. So now it's like the frequency you hear one, like, so this is, you are the observer, this is what you are hearing. This is like when approaching, when the train is approaching. When the train is moving away, okay, away, let me use approach and away, you are hearing 800 Hertz from you. So how fast was the train moving? So now the speed of the source you are asked to determine. So students may say like, speed of sound is given, but the frequency of the source is not given. Then how are we going to find or solve this problem? So the speed of sound usually represented like with no subscript is given 340 meters per second. So the only way that you will find the answer for this one is like, you write f, the observer equation, one for approaching, as we said, like if it is towards, then you will have to use a plus sign in the equation. Okay, so we know that the source is the one that is moving, right? So since the source is the one that is moving in this particular case, then the equation that you will apply is, this one, f of the source into v of sound divided by v minus vs. So we're going to leave vs as a minus because vs is positive when source is approaching, right? And vs is negative when source is moving away. So for this, like if you replace the values, then 1000, fs, you don't know fs, v, you already know v, which is 340. It will be 340 minus vs. Okay, but this equation has two variables, so you cannot solve it the way it is. So go for the other one. So f of frequency heard by the observer when it's going away. So it will be fs, but this time v over v minus vs. Why? Because vs is negative when source is moving away from the observer. Okay, so when that happens, you are hearing 800 for the same fundamental frequency of the train, v 340 again, which is 340 again, but you will have plus vs. Minus of minus will give you a plus. So we had one equation here, we have another equation here. then you have two equations and two variables, you can solve it. But thing is, like, how am I going to solve those two in a better way? Because what I see here is like, I see fs here, and then if I see fs here, you can do simultaneous and whatever, but now I'll go to a little better way to do it. What if I take the ratio between the two equations? So I'm going to get the following. I'll have the left hand side ratio is going to be like this. The right hand side ratio is going to be like this. Okay. See? Just simply take the ratio of the two. Then I'll have fs cancelled out with fs. And you know that dividing two factors means multiplying the denominator by the reciprocal of the numerator, right? So that means this is going to be like this: 340 minus plus vs divided by 340. What I did is like just took the reciprocal of this guy. The two are the same. So this 340 will cancel out by this 340. So therefore what you are going to have is like, you can also simplify this if you want to. 2 zeros cancels out 2 zeros here. So we'll have 10 over 8 can further be simplified by 2, which will be 5 over 4. Okay, will be 340 vs plus vs divided by 340 minus vs. See, over here what's left is this on the top, and on the bottom what's left is this. Okay, so from here what you will have is like, you can do crisscrossing whatever you want, but you will have 5 times, if you do crisscrossing, 5 times 340 minus vs equals 4 times 340 plus vs. It's like taking this to this side and taking this to this side. So you'll have here the 5 is common and it multiplies both of the numbers in parentheses. Okay, 5 times 340 is 1700 minus 5 vs equals 4 times 340 is 1360 plus 4 vs. Okay, so I'm going to take this 5 vs to the other side of the equation, and I'm going to take that number to this side. So I'll have 1700 minus 1360 equals 4 vs plus 5 vs. Okay, so 1700 minus 1360 will be 340 equals 9 vs. 4 apple plus 5 apple will give you 9 apple, right? So divide both sides by 9, then approximately the value of this will be 37.8 meters per second. See, you can find Vs without just simply finding the fundamental frequency. If I asked you the fundamental frequency, then of course you would go ahead and find that fundamental frequency, but not like without doing that. If you followed the ratio property, and then it's gonna take you there faster way. Okay, number 7, sound with a frequency of 1000 Hz moves towards a listener who's at rest. So then it's the source that is moving at 50 meters per second. So the observer is not moving, it means it's at rest. The velocity of the sound is 340. Now the question is, it says like toward. As soon as it says toward, then we are going to use a Vs positive value. Okay. So now what is the observer's frequency? This is a direct application of the equation. F naught, or frequency observed by the observer, equals frequency by the source into V divided by V minus Vs. So F naught will be equal to Fs is 1000, V 340 into 340 minus Vs. Your Vs has to be positive and you have to take it as positive. So therefore you can find V naught as 1000 times 340 divided by 290. Okay. Simplify that frequency, then you should get something more than 1000 because it's moving towards the source. So therefore that value is going to be 1172.4 Hertz. Okay. Great. So number 8, it says 500 Hertz whistle. So that means the whistle means the source. So the frequency of the source is known as 500 Hertz. Is moved towards the listener at a speed of 10 meters per second. So the velocity of the source is known as 10 meters per second. It says towards, keep in mind, towards the observer. When the listener moves, velocity of the observer is now at 20 meters per second, but it's moving away. Then now what is the apparent frequency heard by the observer? This equation, or this problem, it involves both items moving, the source and the observer. Okay. When that happens, the equation that you will want to apply is frequency by the observer is equivalent to the frequency of the source into V plus V naught divided by V minus V naught. I mean Vs. Okay. So therefore your V naught is going to be frequency of the source is 500, V 340 plus or minus. You will be using a minus here. Why? Look, this one says away from the source. So therefore, since it's moving away, then it has to be 20 minus 20. You divide that by V, which is the speed of sound, minus the source. I mean, the source is moving towards. So both of them are moving, just one is chasing after the other, kind of. So if it is toward, then therefore you will use a positive value again. I mean a positive value for that. So the positive, then in that minus equation you just leave it the way it is, but which is 10. So the apparent frequency is going to be 500 into 320 divided by 330. So F naught is equal to, if you plug in those numbers in your calculator, then approximately you are going to get 384.8 Hertz. No, 400, sorry. Okay. So which is less than 500 because the the listener moves away at a faster rate than the source is approaching him. So there is like the frequency, the apparent frequency will be less. Okay. So number 9 is somehow probably a problem that involves both moving, the source and the observer. Two cars, one in front of the other, are traveling down the highway at 25 meters per second. So the car behind sounds the horn, which has a frequency of 500. So the frequency of the source is known as 500 hertz. What is the frequency heard by the driver of the lead car? So V, which is the sound, 340 meters per second. So both of them are moving at 25 meters per second. But the thing is, let's try to have like some kind of so let's say car 1 is here and car 2 is here. Okay, so this is your observer and this is the source. So if you look at the diagram, the observer is moving away from the source. This is away, of course, you can see that, like, but if you look at the source, which is moving towards, so as a result, in our equation, then the velocity of the source is going to be positive, whereas the velocity for the observer is going to be negative, because one is chasing after the other. So when you run after another person, what happens is, like, you are trying to approach him or you are running towards him, but the other person is moving away from you. See? So having said that, like, the equation that you will want to use, FO will be Fs into, the general equation, because both are moving now, V minus Vs. Okay, and both are 25, right? So 25 meters per second, and this one is also 25 meters per second. So F0 equals Fs is 500 hertz into V is 340. So the observer is moving away, then as a result it's going to be minus. Okay, of course the equation is plus, but minus 25. V again 340 minus of plus, so positive in here, 25. Okay, so you'll have 500 into 315 divided by 315. So the two will cancel each other. So therefore, the observer will hear literally the same frequency as that of the source. Well, it does make sense in a way, because, like, if the two are just running one after the other at the same speed or at the same velocity, it's just like the amount of wave that is crossing. So there is no any increment or reduction in terms of distance between the two. So the two cars are going to move like the same distance between them after 1 second. They were, let's say, 100 meters away from each other, like that. After the second, they are still, the gap between them is like still 100 meters. Okay, so that means the wave crosses that are traveling right from the source towards the observer, they are going to be the same. He's going to encounter the same number of frequencies or wavefronts as if those two are basically standing. Okay, so that's pretty much it. This is the end of chapter 14. So until next time, bye.